from George Mason University, who's going to tell us about derived differential geometry and applications to field theory.
Okay, thanks very much for the invitation. Pleasure to be here. I'm glad to be able to give a bit of a longer talk so I can maybe get to where I want to get. Still not guaranteed, but I'll do my best here. So I'm told to be gentle in the beginning, so I'll first try to just motivate. So like, let's give some basic, I'll call some basic facts from differential topology to start. So suppose that I'll follow the same example. So suppose that I have, say, some smooth map of manifolds. And then I have some point, say, some point y. Right. So a basic fact that you learn in the very beginning of differential topology is that so if F is a submersion, can everyone read this back there? It's not very big, but I know the room isn't very big either. So then, so the pre-image is a closed submanifold. So this is, used all the time in differential topology. Now, on the other hand, well, for any smooth F, I can look at this pre-image, and it's at least closed. So this is because F is continuous. And conversely, say, given any closed set, any closed subset, so C of M, it is the zero set of some smooth function, right? So C is equal to, say, like constructive function if you want. The image of zero for some smooth function. So this is telling you that, if you have submersions, well, then you can take level sets and you get nice manifolds. And then if you relax just general smooth function, you can literally get anything. I mean, anything which you could get with continuity, so any closed set. So closed sets can be wild, can look nothing like manifolds. So all bets are off to try to do differential topology with some arbitrary closed set on its own, right? Okay. Then be very far from a manifold. Okay. Okay, but I mean that's in general, but sometimes it's true, right? So sometimes F is not a submersion, but this level set is still a manifold. But it's usually wrong. Okay, so what I mean by wrong, so for example, if you try to look at right, suppose I have f of x equals x squared, so f going from R to R, right? So at zero, it fails to be a submersion, and the zero set is just this single point. But generically, if I were to look at, say, instead, what's supposed to be a parabola, instead, another parabola just slightly down, then I would have 2 points of intersection. So really, this point should be counted twice somehow. Yeah, I mean, it's a double root. So we get the wrong counting. So we get the wrong counting here. Okay. And another kind of example is if I take a point sitting inside, say, R, and I intersect it with itself. So for example, I take a 0, right? Well, the intersection is just a single point, but really, it should somehow be 2 points. Okay. Okay. So, so more generally, as you probably know, instead of just looking at, say, level sets, we can look at, say, fiber products. So suppose I have, say, M goes to L and N goes to G, and these are just smooth functions. So this is, say, a diagram in manifolds, say the category of C infinity manifolds. We say that F is a transverse to G if whenever we have a point X and M and say Y and L such that say F of X is equal to G of Y, and let's just call that point P for simplicity of notation. If I look at the image of the tangent space of M, and I look at the image of the tangent space of N, that together these span the tangent space of L. Okay, so we write this. So we write this as like this because this is a good example of a transversal intersection. So F's transverse to G, and in this case, if you look at, say, the points X, comma Y, and M cross N, such that F of X is equal to G of Y. Now this sitting inside M cross N is a closed submanifold. And is a categorical fiber product. So if I were to make, say, N a point, then we just recover the notion of a submersion. Okay, so particular examples of fiber products, of course, intersections, and that's an operation you want to do in geometry a lot. So if you have Lacquet's universality, it can cause you a lot of problems and create some singularities. So let's look at example. I guess I can continue. Is this a good idea to do or not? People usually do that.
Up to you.
All right, we'll just go for it. Yeah. Oh, live life on the edge. Okay. So now the say geometric example that you often consider when you're trying to construct different moduli spaces. So you have some, let's say you have some vector bundle over a manifold, and we have some section. So lambda is some section of this vector bundle, and we're interested in the zeros of this section. Yeah, so we want to look at lambda inverse of 0, or more precisely, we can look at the fiber product where I have our given section, and then we have the 0 section. Is really kind of an intersection, right? So we're looking at, say, like Z intersect lambda, or the graph of lambda, really. Yeah. Okay. Now, if lambda is not transverse the 0 section, and this the zeros of this section can be very singular. Okay, and lots of moduli spaces are constructed in this way. So, I mean, this has caused some issues. So let's look at an important example of this. Okay, now I see the problem in my ways, because now I have to cover that up to use the next one. So I won't be continuing this experiment, but okay. All right. So suppose that I'm just given, say, some smooth function. And then I can look at, say, the cotangent bundle. And then I have df. Yeah. Well, then, but first of all, what you could have been writing is df, the inverse of 0. This is the critical points of f. Yeah. So those are the points, where the derivative vanishes. So this is called as, say, f. And now the condition that we want to have a nice manifold structure is transversality, right? So df is transverse to the 0 section. This is true if and only if the Hessian of f is non-degenerate on the critical points. Okay. So this is, a little exercise in geometry. And, well, there's another name for such function. This is f is, say, Morse. Okay. So, and in this case, and so we will say if f is Morse, then, well, first of all, you can say crit f is a manifold, and it quotes is not really necessary. It is a manifold, but it's discrete. Yeah, just because of dimension counting. So it's 0 dimensional. So it's just discrete. Okay. But if it's not, well, then it could just be some arbitrary closed set. Yeah. So that's an issue. Okay, so I'll just pretend this is in here. Okay. Now, usually you need more stereo, say, on compact manifolds. And in this case, you don't just have discrete, but you have it's a finite set. Yeah. So if M is compact, and F is Morse, right? This implies that, say, F is finite. And if M is oriented, and all my manifolds are without boundaries. I'm just going to emphasize that. Then we also have, in this case, there's something called the stationary phase approximation. So if, say, mu is a volume element, okay, so we'll just write this. So there is a stationary, I'll put this in color. This is what I'm explaining. The exact form isn't super important. I mean, the exact formula, but the form is more important. Namely, of okay. So let's first say this. Let's take alpha. This is going to be some, say, a real number, and then we take e to the I over alpha f of x, say mu x. Mu is my volume form. So I'm interested in this integral, but I want to understand it as alpha approaches 0. So it's highly oscillating. Yeah. So then this is, I'm going to approximate it by a sum, that's a bad sigma, a sum of the critical points. So let's say like y in it f, and let's see if I can write this correctly. So we have like I over alpha f of y times n minus 2 lambda of y. I'll explain what this all is in a second. I over 4, and then something which I'm not even going to say exactly what it is, but it's a y. And I'll put a comma k, so I was going to have some dependence on k here. Alpha. So this is some explicit numbers which you can describe. So first, and say a dimension of m is n, and this is to the order of, say, alpha n over 2 plus k as alpha goes to 0. So if you want to get better and better approximations, you can do so. So this gives you a kind of asymptotic expansion. Okay. But for this to hold, you need that f is Morse. In other words, you need a Hessian to be non-degenerate at the critical points. Okay. And then you can write this as this finite sum. Okay. Okay.
F minus.
Oh, this m minus 2 lambda of y. I forgot to say what lambda is. This is just the index of the critical point. Okay. Thanks for catching that. I meant to say that. Okay. Now, this seems kind of arbitrary if you haven't seen this before, but there's a very similar looking integral that physicists like to consider, right? So in quantum field theory, one is interested in similarly looking integrals. And so in, say, computing Feynman integrals. Like, for example, a partition function of a theory. So you have some integral, and it's over some infinite dimensional space of fields. And well, and for just a partition function, it has an easy form. Okay. Now, of course, it's problematic to make sense of this with sophisticated ways of trying to do so. But one way that one would hope to try to do so is to just apply this formula, but replacing this with some integral over like the critical points. Hope for the best that you can make sense of those. You replace obviously the sum of the integral, but even to try to do that, you would need that the Hessian of S be non-degenerate. Yeah. So the hope is to apply stationary phase to calculate / define the above, and really only define it, say, perturbatively in this expansion with H bar. But to even do that, you would need that the Hessian is non-degenerate. So here's the problem. is to do so, we need that the Hessian of this function to be non-degenerate. And it almost never is in physical examples, for instance, gauge theory. So I guess for like Star Wars, and we have like the New Hope, right? But that's not like the best of them, but come on, it's one of them. Is that derived geometry will save the day. And we can have a hope for that because of the fact that really this non-degeneracy of the Hessian has to do with non-transversality of an intersection. Yeah. So if you go to derived geometry, you can like fix these non-transverse intersections in some sense by deriving them, and you can hope to try to make sense of such things. So, okay, well, that's kind of like a brief kind of motivation. What am I doing on time here? Okay, great. So I'm going to go to part 2. I'm going to talk briefly about graded geometry. And graded geometry will give you a way of trying to make sense of a smooth version of 0 sets of sections of vector bundles. Okay. And later we'll see how to make this rigorous. Okay. But I mean, graded geometry is rigorous, but making sense of that as the derived intersection that requires, well, some definitions and some more sophistication. So the idea behind graded geometry is the following. So manifolds, right? These locally look like vector spaces. Yeah. And they're spaces which are locally linear. Yeah. So graded manifolds are locally graded vector spaces. Okay, but like, what on earth do you mean? Well, the vector space, at least we know how to talk about geometrically, right? I mean, if it's over R, we can just say, okay, it's Rn, and we can do, analysis on this. So what about a graded vector space? You have to have some way of viewing a graded vector space as kind of a geometric object. Okay. So, well, here's one way to proceed. So let's say that V bullet is some Z-graded vector space. Okay. So, and let's say over R, and let's say that it's globally finite dimensional. So, I mean, the direct sum of all the VIs are, I mean, you might be even thinking about it as a direct sum. I like to think about it as different pieces, but they're equivalent. Otherwise, your morphisms have to be homogeneous. So I'll notice that whatever V naught is, yeah. So in fact, I'll put this down here since I'm going to have some superscripts later. It doesn't really matter. So V naught, this is a isomorphic to Rn for some n. So this we can make sense of geometrically. And now we have to know what to do with the rest of the data. So what you can do is use the rest of the data to put a structure sheaf on Rn. Okay. So let's define O of V dot as the sheaf that for U an open subset of V naught OV dot of U. Well, on one hand, I need to be able to take smooth functions on U itself. And if I were to take regular linear algebraic geometry, or if you're just not used to that terminology, just polynomial functions on V naught, that would just be sim of V naught dual. That's one way of writing a coordinate free. And then we can take sim of V. So here I have V naught, and here I have V bullet dual. But here, this is the graded sim. So this is a graded symmetric algebra. Okay. Well, let's write what this is if I choose a basis, because that'll make it more palatable or more geometric. Maybe more familiar if you're used to doing differential topology. So choose a basis, say EI1, EI2 to EI and I of VI for each I. And then let's see a dual basis. So I'll just write psi I1 to psi I and I. Okay. And then I'll give these symbols degree minus I. Okay. So even though these, so I mean, the reason is these are, VI is in degree I, so the dual ones should be in degree minus I. And we look at, well, we go at it this way, OV dot of U. This is, you take smooth functions on U, and then you would join these variables, I1 through sigma I, and I not equal to 0. And here we just take polynomials, but it should be graded polynomials because these are going to obey the causal sign for commutativity, right? So it's super commutative. Okay, so you just have these extra graded coordinates around. Yeah. Okay. And now this is so this makes, say, V naught comma O of V dot. Gonna put the duals here. Yep. A ring space. Okay. So we have, I mean, it's locally ringed once you reduce it, so to say. If you kill the you just kill everything that's non-degree 0. Yeah. Kill the ideals generated by stuff that's non-degree 0. Okay. So now we know how to talk about graded vector spaces as some geometric object. So that means we can define a graded manifold, just anything which locally looks like that. Yeah. So I mean, because if you kill everything, you're just gonna get it.
No, sure, but you can whoever.
So here, but like what I mean. Sure, fine. Like, I mean, it's not much to what I'm saying unless we go to the graded manifold, which I'm going to say. So a graded manifold is and I'll put in parentheses locally in the sense that I just explained, ring space, say M comma O of curly M. I'll call this thing curly M. Locally isomorphic to, so let's call this whole thing just say V dot underline. So V dot underline for some graded vector space. Okay, so easy enough, yeah? And just a remark, you can do the entire thing I just did, replacing Z with Z2, yeah? And I mean, the only thing that changes is that I'd have only V0 and V1, yeah? So you'd end up getting C infinity U tensor in exterior algebra on V1, yeah? That's, if you've seen before, definition of a supermanifold, yeah? So replacing Z with Z2 gives supermanifolds. The only real difference here is that I can have even coordinates, which therefore commutative, where I only take polynomials of them, yeah, rather than smooth functions. You can make a theory you take smooth functions, and you can create an equivalent category where we have supermanifolds with a certain action, but it's just a different way of expressing it. Okay. Now, let's give an example. So, okay, might have to speed up. Okay. Well, suppose that I have some vector bundle, just in the world of manifolds. Yeah. Okay. So locally, E is just isomorphic to M cross, say, RK for some K. Yeah. So you can make sense of a graded vector bundle, which is, I mean, something locally looks like E and then some graded vector space. And then linear maps just can be the maps which are induced by maps of graded vector spaces. Yeah. So you can make sense of graded vector bundles. And the only thing you can do with graded vector spaces is you can shift them, yeah, by one way or another. So that means that this is functorial, that you can apply this to a graded vector bundle, to the fiber. A regular vector bundle is a graded vector bundle, so you can apply this, yeah. So you can shift fibers of E to get, say, E, say, shifted by I, which is locally isomorphic to M cross RK shifted by I. And this just has RK in degree minus I. Okay, that's a convention. So, okay, but this is now a graded manifold. Okay. So a particular important example of this is when you just shift by 1 or minus 1. Okay, and we're going to be looking at case of minus 1. So if I is equal to minus 1, that's putting the fibers into degree 1. Then E shift at minus 1. That's a graded manifold. The underlying space is just M, but it has some structure sheaf which is different. And the reason is because if I have a vector space with V naught is a point, then the underlying space is a point, right? So what this sheaf is in, say, degree minus dot is going to be sections of the dot exterior power of E dual, because the exterior, like the exterior algebra is just the the shift of the symmetric, this symmetric algebra of the shift. Yeah. Okay, and that's something very concrete. Yep.
This case of economic, what is the bullet here?
Where there's no V bullet here. Oh, sorry. V bullet is E shifted by minus. Oh, sorry. Ah, sorry. Yeah. Okay. Here. So right, I have to say it locally like this, right? So, on the local trivialization. Of E, right? Then this would be, say, smooth functions on U tensor the exterior power of, say, RK dual. Yeah, and that's smooth functions on U tensor sim of RK shifted by, I guess, one dual, let's see, shifted by -1 dual. If I'm doing the counting right, because I also have this minus sign. So that means that we're looking at, well, Rn, where that's the base of m, and then that's in degree 0, so that's V0, and then V1 is just Rk. Okay. So locally it looks like that. Okay. So, first of all, so from now on, all graded manifolds have their structure sheaves concentrated in non-positive degree. So that means that the gradient vector spaces I'm using are non-negative degree. Yeah. The definition I'm about to make still makes sense, but I don't want to have to keep saying non-positive graded DG manifold. So a DG manifold is a graded manifold M with a degree equals +1 vector field. And by that, I mean derivation of its structure sheaf. It's called Q, such that if I look at the graded commutator, the graded Lie bracket, so because this is graded, this is not automatically 0, because it's not Q squared minus Q squared, it's 2Q squared. But this is 0. So it's like you can integrate the distribution, if you will. Okay. So just a remark is if you unwind what this means, so we have a derivation of degree 1 which squares to 0. That's just giving you a differential on this graded commutative algebra. So this makes say O of M comma Q a sheaf of CDGAs over R. So let me give you one example of that. So I'm going to work off this example here. So suppose I have just a vector bundle over an ordinary manifold, and I'm given a section. So on E shifted by -1, let's let U be insertion with respect to lambda. So how does that make sense? Well, the structure sheaf is exterior algebra of the dual, right? So you can insert that a section of E into exterior algebra of E dual, okay? And because this is exterior, that automatically squares to 0, yeah? So this is, so like E bracket -1, insertion lambda, this is a DG manifold. Okay. So I claim that this DG manifold is modeling the derived zeros of that section. So now that's not a rigorous statement at this point, but it will be. But here's something that actually maybe first I should point out the following. So in local coordinates, say if psi 1 through psi k is a basis for the dual of the fiber of E. If I look at O of E shifted -1 Q, then, well, we have smooth functions, say, on U, and I add in these coordinates. And these now are in degree -1, and then I look at Q. This is just lambda I partial psi I. Yeah. That's what the insertion does. And you might recognize this is a causal complex. Yeah. So if lambda is transverse to the 0 section, then these lambda 1, lambda 2, etc. gives you a regular sequence. And then we know that this is, so that's quasi-isomorphic to just, well, killing the lambdas. So that means there's only cohomology in degree 0, but in that case, if it's transverse, we know that the 0 is a manifold, and we get actually that manifold. So if, say, lambda is transverse to Z, then like smooth functions, if you will, on E -1, comma, I lambda is quasi-isomorphic to smooth functions on the manifold of zeros. And in general, even without transversality, if U does not intersect the zeros, then O E shifted -1 of U comma I lambda is a cyclic. So all the information is concentrated around the zeros. Okay, so that's kind of like an idea that maybe this is modeling drive intersection, but that's not like it's not like a rigorous anything. It's just kind of like a remark. So, okay, and what, I have about 5 or so minutes, is that right, until the break, or do I choose?
Yeah, it's up to you.
Okay, so I will, yeah, with like 5 or 10 minutes, yeah, so almost on pace. Okay. So let's do part 3. And part 3 is going to be some motivation from field theory. So I'll start off with classical field theory. So the setup for classical field theory is we have some fiber bundle. It's called the configuration bundle. And then we say the space of fields. Sections of this fiber bundle. That's why I was remarking that it was infinite dimensional. And then we have some action functional. And I'll write it the way the physicists usually do, which is just you write it, except I won't use coordinates, right? So I'll write like this. So it's some integral over the base manifold of some density or top form of the Lagrangian density. Okay. And the classical field configurations are those which satisfy the so-called Lagrange equation. So these are the critical points for this action functional. Okay. So the classical field configurations are the critical points of S. So, so in other words, if we look at the variational derivative of S, when we evaluate it phi, then this is 0, and this is called the Euler-Lagrange equations. If you want them in the, say, normal form, you usually first see them, you just assume that L only depends on phi and phi dot, and then you can write it explicitly. Well, say dot would be if it's, say, over R, but phi in its first derivatives. Okay, and then important among these, the ones most important for physics, would say, besides, say, classical mechanics, in which case you would take M to be, say, 0, 1, or R, and then this would be space, and looking at trajectories as your fields. Would be gauge field theories. So, whoops, this is gone. Okay. So, gauge theories. So they start with a little more input. So you have some Lie group and a principal bundle for that Lie group over a manifold. And then we, so this is a principal G bundle. And then our configuration bundle is the affine bundle of connections. So connections. So if P is trivial, which is often the case, or even often assumed, then this is, of course, just T star of M, non-canonically though, on T star of M tensor with Lie algebra. Yeah, so Lie algebra valued one forms. Yeah. Okay. And then, well, the fields. This is so this is F. This is just, well, the principal G connections on P, and then really this ought to be modulo gauge transformations. Okay, but I'll talk about that towards the end. Okay, so some examples. Okay, so maybe I'll just, for time's sake, I'll just mention, so without writing anything. So 3D Chern-Simons, a nice mathematical example, which also has applications to solid state physics. And there's also, say, 4D Yang-Mills. And this explains all of the fundamental forces of the universe besides gravity. So I mean, G is U1, we get electrodynamics, and then if it's SU2, we get the weak nuclear force, and SU3, we get the strong nuclear force. So these are, I mean, from physics are super important. Okay, so so I want to just have like 3-4 minutes, and then I'll have a break. Is that cool? Okay. So this is like, so let's look at like a kind of toy example of this, yeah? So, right, before I do that, I just saying classical, so let's go first of all to quantum. So, so if I go to quantum field theory, so if we look at quantum field theory associated to classical field theory, so we're going to do the following. So suppose that, say, O is a quantum observable. So it's some measurement you can make on your system, and you want to find the expectation value. So the expectation value is often expressed as an integral over the fields. So phi and phi, and then we have O of phi, then E over I H bar, S of phi, then divided by, if you want, normalized by this, where this bottom part is a partition function. Okay, now, I mean, this is problematic, like to make sense of. That's like one of the main parts of the game, but we can just pretend that the fields or an compact oriented M manifold just for a moment. Yeah, and to see what we can do. So that would be if M is a point, if you want. And toy and E is compact. So for example, that F is a closed M manifold, and then choose a volume element mu, which is sorry, to play the role of this measure on the space of fields. Okay. So first of all, notice that if I have a volume element, let's also assume that this is, say, oriented, just to make life easier. Okay. Well, that gives me an identification of, say, smooth functions with n forms. And more generally, I can, so I want to go this way. If I look at, say, multi-vector fields, so say I-fold multi-vector fields, I can identify that with n minus I forms on F by contracting with mu. Okay, so we get these canonical identifications once I choose a volume element. Okay, and now I have a Derived differential here. So I'm going to go to the mu of, well, right, n plus 1 minus I. And this is going to be identified with I minus 1 fold vector fields. So this induces something which we call the divergence operator. Okay. And since this squares to 0, this squares to 0. Yeah. Okay. Okay. So this implies that I get a, well, if I put things in minus and negative degrees, I still get a cochain complex. This is a cochain complex. And then H naught is isomorphic to Hn, the realm of F, which is isomorphic to R, since it's a closed origin and manifold. Yeah. Okay. So now this also works for so e to the I over h bar s times mu, or s, say some smooth function, but we just replace, say, R, C. No big deal. Yeah, we can run the same game. Okay. And here's a calculation. You just use this Barton's magic formula. If I look at I h bar divergence of mu mu s, so let's call this thing mu s, then this is equal to I h bar divergence mu plus insertion with respect to ds. Okay. So if we let h bar goes to 0, then we get, well, something looks like this. And I'll write it suggestively. So P star of M star, and then insertion respect to ds. And this is just smooth functions on, if you want, R ds inverse, right? So this is this derived critical locus that we got from the DG manifold. Yeah. So the derived intersection of ds with the zero section. Okay, so I'll just say this part in words because for time's sake, but if we leave the h on, then we get a deformation. Yeah. And so we get an operator, which is called the BV Laplacian. Okay. And we form something called the BV algebra. So what you could do in general is you could try to, if you could find the algebra of functions on the derived space of solutions, you could try to perturb it by finding a operator to play that role and give you a BV algebra. And that's the basis of BV quantization. So I'll stop there for the break, and then I'll do like some real stuff. Okay. So, all right. So this is a secret. This is the first time I've ever had 1, 2, 3, 4 in a talk. I usually just here's everything. So should be proud of me. I know I am. Okay, so far everything is in background, and we also, well, maybe not heuristic because I didn't say anything wrong, but it's just maybe not to make precise statements. Yeah. So let's try to take all that and make it into real math. Well, it is real math, but make some theorems and stuff. Make a formal framework where we can make sense of this stuff. So let's talk about derived manifolds more formally. So first of all, I never even used the term derived manifolds the whole time yet. I just talked about maybe a derived intersection. But the idea of derived manifolds is, well, things that you get where you start from just taking manifolds and then taking pullbacks of smooth maps, which may not be transverse, but you want to do so in a smart way. And then maybe you can then continue and then have smooth maps between those and take pullbacks and then do this finally many times and see what you end up with. Okay. Let's try to formulate this in terms of a universal property. So we'll start with manifolds, a category of manifolds, and I'll write here the one category of manifolds, because sometimes people are like, wait, you're not taking the spaces and morphisms. No, I'm not. Just taking smooth maps. Okay. And well, a lack of time, I can't fully justify this, but we're going to take derived manifolds to be an infinity category. And the quick reason is if you want pullbacks to behave well with respect to Comaldi, for example, borders in theory, if you're in a one category, you would be forced to have a point intercepting a point to give you a point, and that breaks things. Okay, But you know, this isn't the case, say, in an infinity category, like in spaces, I have a point instead of a space, and I intersect it with itself, I get the loop space, loop space, right? So, which need not be contractible. Okay, so now this infinity category, it should have finite limits. Because I want to be able to take fiber products, and it should also have a terminal object. So yeah, then that means I have finite limits. Now this should be a functor. Now I mean, you want to ask it to be fully faithful, but it turns out you don't even need to. It becomes automatic without asking it. So let's just leave that out. Let's call this functor I, and let's say that I needs to preserve transverse pullbacks. So anytime I have a transverse intersection, I want that to still be the intersection in the derived manifolds. Yeah. And the terminal object. So I mean, there shouldn't be like no one reference from a derived manifold to a point, because that would be really weird. Okay, well, that's kind of like a minimal requirement here. But now I ask that this to be universal with respect to this property. Okay, so in other words, well, I'll say this in a way which, you know, if you know infinity category theory, you'll get mad at me, but then you'll also know exactly how to fix it, so then you shouldn't be mad at me. But so I'll say for all functors f from to C with C any infinity category, say with finite limits, with f preserving transverse pullbacks, and the terminal object here should exist unique. Of course, this is the part I should really see contractible choices, right? But let's try to make this simple. Unique f tilde, extending this such that f tilde preserves finite limits. Okay, so this is a universal property. Okay, so this is like a natural thing to try to guess, right? Because it just like tells you that you're building broad manifolds, forming out of manifolds by doing pullbacks, and you want to keep the transverse ones. Yeah. So, of course, this is completely characterize this up to equivalence, but if you can't say anything more about it, then it's kind of useless. Yeah. But you can say more about it, and that's what's cool. So it's turned out to be, say, the right guess. Okay. So, okay, so first, let's try to, we'll try to make this more explicit. And we'll first try to connect this with derived algebraic geometry. Okay. So how to connect with derived algebraic geometry. So, I mean, roughly speaking, derived algebraic geometry. Now I'm not going to be talking about special, so I'm going to be on characteristic 0. So let's just take just algebraic geometry over, say, actually, you don't even have to say characteristic 0. Yeah, say simplicial. But if I'm characteristic 0, I can say differential graded, and then commutative algebras. So this part is characteristic 0. Okay. And then these are non-positively graded if I'm using homological conventions. Okay, so connective CDGAs. Okay, so question is how to view differential geometry or differential topology as algebraic geometry of some flavor? That's a natural question. Okay. So to do this, there's a natural thing called a C infinity algebra, sometimes called C infinity rings. So first, heuristically, a C infinity algebra is a commutative R algebra, A, with additional n-area operations, say A to the n A, are all smooth functions from R into R, with, of course, natural compatibility between them. Okay, so you have it's a commutative algebra with extra structure. Okay. So more formally, and before I do that, actually, this is a prototypical example. So a prototypical example is if you just take smooth functions on a manifold. Yeah. So notice that smooth functions on the manifold to the n, right? So I'm trying to describe this. Well, this is just smooth functions from M into Rn, right? So I want to describe this, and well, I'm just going to take psi, which goes from M to Rn, and I'm just going to send it to F composed with psi. So that gives me an n-area operation. Okay, it's something very simple. Okay, so how do I make sense of this in a nice way? How do I phrase that? So formally, so let C infinity be defined to be the full subcategory of manifolds on, say, a point R0 and then R2, right? So all the Rn's, yeah? So a C infinity algebra is a finite product preserving. Oh, I was told not to use blue. Okay. Functor. I'll maybe write this say curly A from C infinity to sets. So notice that R is a commutative R algebra object in C infinity, right? Addition and multiplication are smooth, right? And so is, scalar multiplication. And all we need to express that is finite products, right? So this implies that A of R is a commutative R algebra. Okay, so that's how you encode this. We have A to the R, and then if I have any smooth function, say from R into R, that gives me something from this to the n to itself. Yeah, and the fact it's a function, it tells you that we have this natural compatibility. Okay. Okay. So I mean, if you know about algebraic theories or review theories, it's just a special case of algebraic theory. So more generally, if C is any possibly infinity category with finite products, we can say that talking about C infinity algebras in C, and these are just going to be the finite product preserving functors from C infinity into C. This just means finite product preserving. Okay. So, right. So just some, so what makes these, a worthy concept, is that a whole lot of stuff from commutative algebra just directly works. And probably the most, okay, well, there's a few things. So first, though, if I look at smooth functions on Rn, this is now a free algebra. So this is, or I like to write it like this. So free C infinity algebra on n generators. So this is pretty nice, yeah? I mean, more from the C infinity algebras into another one is just same as picking out n elements. But one of the most important things is more generally, so if A is any C infinity algebra and I an ideal of the underlying ring, then A mod I is canonically a C infinity algebra again. Okay, so the notion of ideal doesn't change. That means it's closed not under just addition, but all the operations of the C infinity ring. Okay. And then, so we write the coproduct. So the coproduct in commutative algebra is a tensor product. So we'll suggestively write this like this. So this is the coproduct of C infinity algebras, and it satisfies that, say, smooth functions on a manifold, and I take the coproduct with smooth functions on another manifold, and this is isomorphic to smooth functions on the product, which, I mean, we know it contains, but is not equal to just the tensor product over R if, they're not zero dimensional. Yeah. So this makes this tensor product a lot better. And in fact, more generally, if I do, tensor product over stuff or pushouts, it preserves transverse pullback. So that's really cool. Okay. So what about talking about derived C infinity algebras? So, I mean, that's the same as say homotopical C infinity algebras. A natural choice to do is just look at algebras, but now in spaces. Yeah. So let's take algebras for C infinity, but in the infinity category of spaces. Right. So in terms of model categories, this is the model category of, say, simplicial C infinity algebras. Okay. Now, what's really nice is that there's actually well, okay, so first of all, you can ask, well, what about having a differential graded version? We've been talking about differential graded the whole time. Ring characteristic 0, right? So we should be able to do that. So you can define a notion of a DG C infinity algebra, and we'll look at one's a non-positive degree. So myself and Reudenberg defined this and then put a model structure on here. And then Joost Nouten proved that there's a C infinity Dold-Kahn correspondence. So this is an equivalence. So that's pretty neat. Okay. Right. In the prototypical example here, just smooth functions on M, where M is a DG manifold. So just like the prototypical example of a C infinity algebra is smooth function on a manifold, prototypical example of a DG C infinity algebra is the smooth functions on a DG manifold. Okay, so and a DG C infinity algebra, when you're just in non-positive degrees, it's really easy to say it's just a CGA, but on degree 0, and so it's just a C infinity algebra. So it's additional structure, and then the morphisms have to respect that. So it's like, you know, the most naive thing you could try, and it works. Okay. More generally, it has to be on the 0 cycles. Okay. So, okay. Now, so finally present it. Oh, let's write homotopical C infinity algebras. I'll just define these to be the compact objects. And in here. Okay. Right. So that's a natural thing to do. So okay. So how does this relate to? No, I told you universal product for dry manifolds. I just like forgot about it. Well, let's go back and connect this. So here's a theorem. It says this is myself and Hella Steffens, which says that derived manifolds, so its universal property is equivalent to C infinity algebras and spaces which are finally presented. So it satisfies the same universal property. So therefore they're equivalent. And so this is, I mean, if you will, affine derived C infinity schemes of, say, finite presentation. Okay, so this tells you that whatever derived differential geometry is, it's just algebraic geometry over these derived C infinity rings. Okay, so that's kind of cool, right? Because this is something used with manifolds. These are just, I mean, it's kind of surprising. Okay, now you can also talk about because let's use universal property for a second, right? So here we have manifolds, and so moreover, this map is fully faithful, it turns out now. It becomes from this fact and then embeds fully faithfully. So manifolds, it has a map. Well, first of all, a map to say topological spaces, but you could also, if I want to make this fully faithful, I could say like R ringed if you want. But you could also just put it into, say, top C infinity. So it's like x comma O of x, where this is a derived C infinity ring. Right? It embeds fully faithfully here. And this, it preserves transverse pullbacks. And then we get. So actually, to show this period for pullbacks maybe is harder. So the way that we prove this is we show that the universal property is equivalent to a much weaker condition, namely, well, a priori weaker, that finite product preserving functions from C infinity correspond to transverse different functions which preserve finite limits. So that means that this is equivalent to it, the inclusion just preserving finite products, which is easy. Okay. So we get something here, which under this equivalence, you can, and it turns out to be fully faithful here, is like stack C infinity. So it gives you a spec functor just for free. Okay, and it's fully faithful. That takes some, work, but it's fully faithful. And so you can talk about, like C infinity schemes more generally. Yeah, and you also have the notion of core now, because you can view them as local spaces. So there's a canonical growth and topology there that you can use. So now one thing that we have too is that if I have say a DG manifold, this is just say the one category if you want. Well, there's a functor to, and I'll write it this way, DG C infinity alg, but then I'll put like O to say that I'm like taking the infinity category. Yeah, so and I'll put op. So it's gonna just send this, you say, my functions. Well, the weak equivalences are the quasi-isomorphism, so this is going to send quasi-isomorphisms to equivalences. Yeah, so we can construct the universal infinity category with the quasi-isomorphisms inverted. So, like, move up a little infinity for that, right? So there's a functor like this, and it therefore induces a functor like this. Yeah. So there's a functor from the infinity category you get from from DG manifolds and then positive degrees, where you just universally invert these quasi-isomorphisms. And theorem is that this phi is fully faithful, and the essential image is the compact objects. In other words, derived manifolds. Yeah. So it tells you that this is also, well, not this, but this is also derived manifolds. So these are all different ways of talking about the same thing. So derived manifolds, you have this universal property. You can talk about as finally presented affine C infinity schemes, or you can just talk about GG manifolds. And particularly, it tells you that a higher C infinity ring is going to be finally presented in the infinity categorical sense, if and only if it's quasi-isomorphic to smooth functions on a DG manifold, which is kind of cool. Okay, so right. So now let's actually try to use this to like look at this stuff from field theory. That's what I'm trying to do in the last bit of this talk. Okay. Other questions about any of this? It's okay. All right. All right. Right here. So now we have a setting where we can, formally say all this stuff. So talk about, say, moduli spaces in field theories. Okay, so we will work in infinity topos achieves derived manifolds. I usually sometimes I enlarge it to have some extra things, but just like looking at things that aren't a finite presentation, no big deal. So this is enough for this. So I want to be able to construct these derived spaces solutions to Euler-Lagrange equations. Well, suppose I have some fiber bundle. So I want to consider the sections, and I want to view that as an element here. Okay. Well, one way of doing this is notice that this is in over M, and then there's a canonical geometric morphism, let's call it T, which goes back down So I can just write this as T lower star of pi. Okay, that's just abstract, but that tells you that this is a thing. But what it actually does is something very reasonable. So by Ionetta, it tries to tell you what maps into it are, right? So if I have, say, some derived manifold mapping into functions like this, well, I'll just write this cartoon wise. So it's going to be the space of maps like this. So I have the projection map down to M. I have E, and I'm looking at the space of sections. Okay. Now, this isn't just a set because maps from a derived manifold to a manifold is a higher groupoid. Yeah. So that's what this is. And this is, an n parameter family of sections. That's what it should be. Right. That's what smooth maps into it should be. Okay. Okay. And I mean, another way of writing this is like this is just say sections over n of PR1 upper star if you want. Yeah, so it's not a cartoon. Okay. Now, the main thing we have to make sense of though is what what are we doing this empirical locus? Like, what does that even mean? What are we intersecting? Yeah. So here's an issue is that if you look at this expression, okay, S of phi being this integral over m of L of phi, this can be problematic if m is non-compact. Yeah, it may not even actually make sense, but you can still make sense of the variational derivative, and that's because you're really just talking about variational derivative of electron density. Yeah, so this is the real object. Okay. This density is really what we're after. Okay. So, okay. If we have M as a point, right? So then S, well, of course, does make sense, and S is just going to be a smooth map from F, which is E, into R. And then, of course, the variational derivative is the same thing as just the one form ds. And this is a section of the cotangent bundle. Okay, but let's think about the cotangent bundle. Let's think about this as sorry, you're absolutely right. Well, yeah, this whole thing is not over F. This is going to be F and then F. Thanks. Yeah. Think about this as from TM into R. Okay. Where this is what I'm mapping it to, right? So this is a heuristic argument, I'm going to say, but then I'm going to give it a definition. So so the idea is then, in general, you can think about going from F to the densities on the manifold, or top forms if it's oriented. Yeah. So we want something which I'll call, like, say, the variational cotangent bundle to be like from TF into densities. Yeah. And this is holistically, yeah, but it should pair with TF to give you a density, yeah, instead of to give you a number. Yeah, it becomes a number if you can integrate it. Yeah. So more precisely, So we look at, so we have e's over here, and then we have pi goes down to m, and then we have, so we have the vertical tangent bundle. We can also look at the vertical cotangent bundle. And in fact, we can take this and we can tensor with the pullback via pi of the density bundle. So that's something which sits over E, then sits over M. Okay. Now, one thing that you can check is that, first of all, TF, where F is sections, this is just sections over M of VE. So it's like maps all the way up like that, but we're gonna have VE there instead. Okay, so that's something that's easy to check. And you know, the map down to F, where F is equal to sections of E, is just, well, the obvious one, where if it give me a section of this, I just project down to the section. Okay. So we define T star var of F to be sections over M of VE dual tensor I over star of densities over M, right, which maps down to F. Now, it's a vertical cotangent bundle. So it's a dual of the vertical tangent bundle. Yeah. Okay. So now one thing that's also secretly happening is we always, like in physics, you have the densities of the Lagrangian densities are local, so they only depend on the infinite jet of the section. So, and the Lagrangian density really sits in the variational bicomplex. So that as a top comma 0 form, it's this variational bicomplex. And the variational derivative can be written in source form, so it has a in say omega top comma 1 of E. And now if I have so that means I can write, like, if I look at the infinite jet bundle of E mapping to E, and then I have tells me that you can view the variational derivative as a map like this. Okay. Well, we also have M cross sections of E, which this, of course, is just F. There's a map which just takes the prolongation, yeah? The point in the section, I take it to the infinite jet. So this induces now something here, right? So, and now by the universal property, this, so let's call this maybe this tilde. This corresponds to a section of the dual tensor fiber star density M over sections of ME, right? So I'm just looking at a map M cross something into here. Mapping is just a section, right? So it's a section over this, which by abusive notation I'll still call tilde L. Okay, so this is a map from F into here, and it's in fact possibly nonlinear. It's a differential operator. Okay. So we have a section of this thing which I call T star of R, and the section is even a differential operator. Okay. All right. And that's because it comes from, you know, the infinite jet. So this allows us to talk about the derived critical locus right away, because we can just say will define the, say, sol of L, if you will, like the derived solutions to the field equation associated to L as this fibered product, where I go like this to like T star var F, and I go by F, and then with an obvious notion of a zero section here, and then I just take this pullback in the topos. Yeah. So it tells me what the functor points are. So it tells me a way of talking about like parameters, like a family of solutions to the field equations parameterized by a derived manifold. So that gives you enough information talking about the derived space. Okay, now that's not so bad, but this completely ignores gauge symmetries. Okay, so for scalar theory, like this is sufficient, but it gets much more complicated to do this for gauge theories. So let's put down the last like 5 minutes or so. So what about gauge theories? So this is why, for example, I haven't finished writing the paper yet. I mean, I think have the pieces in place that I can write it, but I mean, it took a long time to get this working. So, oh yeah, don't use blue. Okay. So remember, I have the setup of I have a, say, a principal G bundle over a manifold, and so let's start here. Let's just take, say, the sections, which is say like, sorry, the connections modulo gauge. So I'm writing this very generally. So this is like the big adjoint bundle, but really you're looking at, in the case of a trivial bundle, it's just this one forms modulo smooth maps into G. And you can ask, well, what is T star var of F? I can't go to the same thing. It's not sections over M of anything. Yeah. So what can we do? Okay. So let's first of all note that when we actually had that these fields were just legit sections of something, so we knew that TF is the sections over M of the vertical tangent bundle, and also if I look at T star var F, I look at the fiber over a particular field. So this is isomorphic to sections of the first. So this would be the pullback of vertical cotangent bundle, and then tensor densities. You no longer have that pi upper star because it plays with the phi star and the cancel. And this, you might recognize, this is the same as, and I want to do it this way. So I'll take this dual. So I have the dual tensor densities. That's called the Sear dual. So this is VE, and let's write like dual underscore Sear. Okay. So we're taking the Sear dual. So the fiber, but this is, sorry, of, right. I forgot to put the phi upper star. So, yeah. So T E of F, this is sections over M of E upper star VE, right? So here I have sections of something, here I have sections of its Sear dual, right? So that's what the T star var does, yeah? Okay, now in our case, we have something much more complicated already for the tangent bundle. So the tangent bundle, the tangent complex more accurately, this is, say, at a point, this is here the calculation. So it takes a little bit of work, but you can calculate this to be, well, sections over M of, so here I have, say, the adjoint bundle, and here I have the adjoint bundle tensor T star of M, and then this is say in degree -1, and this is degree 0, and this map is the exterior covariant derivative. Exterior covariant derivative operator associated P. So you can work that out, and this is a complex of, say, C infinity M modules, I mean even vector spaces, and differential operators. Yeah. So this is what, if you will, the tangent space looks like. So we can take the formal adjoint of this differential operator. Okay. So take the formal adjoint. So I'm just gonna ignore the sections part here for a second. So this would go between the dual of this tensor densities, but now the map is going to go the other direction. Okay, and this is going to go to adjoint P tensor T star of M dual tensor densities. But this whole thing is a Serre dual of this. That's how, like, we always have that the formal adjoint goes between the Serre duals. And then we can calculate what this is. This is just a adjoint of P upper star. So using just the combination of densities and cotangent, this is just. So this gives you cotangent and then tangent. This is we get top -1 forms of M. And this here, this is adjoint P dual tensor top forms. And then you can actually show that the formal adjoint is still the exterior derivative, but now maybe with respect to like the dual. Yeah. But in almost all the cases you have some invariant pairing on Lie algebra. So it gives you a way of identifying this with its dual canonically. So then you can smear the difference. And so we're getting parts of this. Well, it would be a complex if it was flat, right? But this, sequence of maps, which is the exterior covariant derivative associated to the connection. Okay. So we want this to be T star var F P, but that's just kind of specifying the fibers. We can't do that, right? But this is like, our motivation. So now, all right, I don't have much time as I'm over time actually. So I'll try to do this quickly, but if I have a complex of C infinity M modules and differential operators, I can view this as a derived D module. Yeah. And then I can take the Verdier dual. So taking Verdier dual corresponds to just taking the formal adjoints of the differentials. Okay. So the idea is then to construct T star bar of F as the fiber-wise Verdier dual of TF. Okay. So here's just a quick remark, which if you were thinking paying real close attention, you might have noticed that we have already an issue though, because if I have an open set, right, of a manifold, I can try to look at this whole thing. So sections over the connection forms on U modulo gauge. This is not a sheaf. I kill it being a sheaf because I've modulo it by gauge. So the fields need to be a sheaf, right? So already that tells us F is not the right thing. Yeah. So we need to actually sheafify it. And it turns out that sheafifying it actually turned out to be the same as working over the Derived stack. So very quickly. So now this is just for the people familiar with the Derived stack. It'll only take like 2 minutes at most. So I have a map from the manifold to its Derived stack. And also the gauge group acting on connections is not fiberwise, but it depends only on the one jet of the gauge symmetry. So this gives us so the bundle of groups I can push to a bundle of groups over the Derived stack, and it acts directly over the push forward of this. So this corresponds essentially to the sections acting by differential operators. And then this is over M Derived. So this should really take, say, F global defined to be sections over M Derived of P mod sections. All right, push forward. And it turns out this is actually the sheafification. So if you were to sheafify F, this is the value you get on global sections. And as such, there's also a canonical map from F to here, and you can prove this is formally at all. So if you want to compute formal neighborhoods, this is good enough. So we can ignore the difference. But if you want to know the global space, we have to do the whole thing. So you can kind of work these off of each other. Right. So then what we can do now is to define the Virtual quotient model. What I can do, let's take X to be this quotient thing over the Derived stack. This quotient stack is like relative to working over the Derived stack. So this is capital add P, right? So I'm going to take, right, one sec. Right. So I take the vertical cotangent bundle of X with respect to its map to the Derived stack, and then I take the relative Verdier dual of this, and this maps down to X. Okay, and so then, and this further maps down to M Derived. So you can say that T star. So T star var, if I wanted to find it over F, I'm actually going to find it over F global. I can always pull it back, right? So then just look at sections M Derived of this. So this is like T star var F, maybe I should say like global. So the final remark I want to make is that because of the fact that our variational derivative actually like comes from the jet bundle, we get that the variational derivative is actually a section here already. So it's over the Derived stack. So in particular, this tells us that so like the derived space of solutions over L, this is actually equivalent to sections over the Derived stack of like, well, this pullback here. So here's X. And this goes to this here to like, it's say relative for your dual this, and then X, and then 0. So the moral of the story is that we're really just looking at stuff which is sections over the Durand stack. And that's how you can construct these in general. And then, you can generalize this for like, higher asymmetries and stuff just by looking at, quotient stacks already over the Durand stack. So I'll stop here.